Let me walk you through the world of large language model in healthcare. So LLMs or large language models are revolutionizing healthcare, unlocking the future. And although language models are trained to predict the next word in a sentence, so basically an advanced autocomplete, new capabilities such as ability to summarize and answer questions emerge out of this complex system without any explicit training, which allows the model to perform strange and unusual tasks such as passing a medical licensing examination or simplifying a radiology report or extracting drug names from a physician's note, replying to patient questions, summarizing medical dialogues, and write histories and physical assessments. So, what makes these LLMs possible? The idea starts with the basic concept of what we call self-supervised learning, which is simple idea of a learning approach where the machine learning models learn without relying on external labeling of the data. So for example, the model generates its own training data set from the information given to it and without need for humans annotating the data that what means what. And this, simplifies the process a lot. Otherwise, labeling huge amounts of data can be a big limitation. So a common type of self-supervised learning is something called autoregressive training objective, in which the model is trained to predict the next word or token based on the previous context or tokens it has received. And that forms the basis of what we consider large language models. So the training is basically maximizing the likelihood that the model or the machine learning system will be able to say, based on the words I've received so far, this should be the next word. The next step is building language skills through transformers. Transform is a deep neural network architecture that is designed to be efficient at capturing relationships and dependencies between elements in a sequence. So, for example, the relationship between words in a sentence, and so on. The training in this manner is often the first stage where the LLM goes through. So, there's often called generative pre-trained transformers or GPT. This is followed by the next step, which is tuning. So getting better at a specific job, so predicting the next word in a sentence in a specific context requires what is called tuning. It's a process of adapting this pre-trained LLM or GPT to perform well on a specific task or domain. This process involves training the model on a smaller but labeled data set, which is specific to a target task. So during this process, the model then adjusts the weights and parameters so that it can predict which token or part of the word or word follows which token or which word. And these weights or parameters are adjusted based on the pertinent models to optimize the performance for those specific targeted tasks. And this is becoming so good now. But in the past, it used to be very difficult. So, for example, GPT-3 was a model that was trained on 45 terabytes of text data containing roughly about 500 billion tokens. So, one token is about 4 characters or about 3/4 of an average word of English. And GPT-4, in comparison, was trained on 170 trillion tokens. When you have to further fine tune it, then you can sometime adopt a model called instruction tuning, where you do a tuning in which training is done on a test data set that contains pairs of instructions and then desired output. So after tuning has been done, you can show, okay, if I ask this question, if this is the sentence and this is the answer, this is the sentence, and this is the next word, and then that further optimizes based on those solved examples on based on those instructions being kind of given how this model should perform. Now, coming specifically to the medical LLMs, there was a recent, very beautiful review done by Warnow et al. That reviewed the training and kind of self-supervision used by 80 different medical language models. And it found it basically fall into two categories. So although general purpose LLMs, GPTs like ChatGPT or Claude, performs reasonably well on many medical tasks, they're not specifically instruction tuned for medical tasks. So medical records can be reviewed either based on what sentence follows which sentence, which word follows which words or sentences, or you can follow it. Okay, if patient A is presenting with cough today, then is often given paracetamol or amoxicillin or something, and this age, this happens. Then same patient, this happens. A patient who has given steroids has diabetes before. later on develops hyperglycemia or elevated A1C. So it's like a time sequence of events of outcomes can be another way of looking at the chart. So you can have medical documents based training of LLMs where LLMs are trained on the document in terms of when you're being documenting a clinical scenario, then these words are followed by these words. So for example, you can give them all the previous charts to look at or PubMed extracts, and based on this word, this follows. This is becoming so good now that research at the Center of Foundation Models at Stanford University, they created a model called Alpaca, which only used about 4% as many parameters as an OpenAI text DaVinci and matching the performance of the GPT-3, but only at a cost of $600 to create. The other category of medical LLMs is the medical codes LLM, which train on the sequence of medical events in a sense of the whole chronological history of a patient. And their ability is to predict, okay, which codes or which problems follows which problems and follows like a time correlation of the progression of disease and so on. So they can, uh, so for example, if you code or give a code of hypertension for a patient, then these models can predict, okay, the patient may go on to have codes of strokes, myocardial infarction, kidney failure, but that's far out. Or you can say that a patient comes into hypertension, often the next code or next event that follows is this blood pressure medication or these medication. And of course, it can gradually fine tune it that if the patient is this age, this location, this past history, or with or without kidney failure, with or without MI, then usually these blood pressure medications are the ones that are picked. And this is kind of and usually the output is not always like a textual documentation, but like machine understandable representation that can be then fed into another machine, such as a coding machine or a machine that generates billing codes and so on and so forth. And this process is called embedding, in which a fixed length and high dimensional vector representing the patient medical record is fed in, and some vectors are brought out of it. To predict, like for example, 30-day readmission risk, and you can predict such as hospital length of stay or inpatient mortality, and so on and so forth.